All right. We're doing the exam review today, right? Primarily because we had the test on Wednesday. And so by doing the exam review the Tuesday before, might not give you a lot of time to study. So, and I know a bunch of your colleagues have 2 exams next week, sort of back-to-back days, 3 exams. So I at least know you have 2. You have one on Wednesday, one on Thursday, so I can at least control that. But this gives you a little bit of a chance to study for the first one and then study for the second one. So it kind of breaks things up a little bit. So the hope is by having this exam here, you start studying today, tomorrow, and then for those of you who have other tests, because I would imagine a lot of folks do have tests next week because it's a university policy thing about not having exams the last week of classes. So it has nothing to do with me. It's just that we're not allowed to have regularly scheduled exams the last week of classes. Now, I can have a non-regularly scheduled exam. So, for example, if for one reason you had for some example, you had a valid reason for missing a test, then I would schedule a makeup test during that week because that's not a regularly scheduled exam, right? That's just because you missed something. And so we put it in that last week, but that's sort of how it works out. And it may not necessarily seem fair, but basically that is what it is. So if you have any issues with it, you need to talk to the administration because it's really not my policy, it's theirs. But we've got 2 major topics we're going to cover. And the first topic is steady state error. We did that almost about a month ago, right? Before break. And steady state error is a really good way to calculate how bad our system is going to be in steady state. So again, it's only a steady state parameter. It doesn't look at things from a transient's perspective. If you want to look at things from a transient perspective, you have to go back to the first order and second order circuits that we talked about. Or when we also did root locus, we kind of revisited the second order circuit when we looked at the damping and all that stuff. So making sure you understand how steady state error can only give you a final value. So it's not going to give you a time domain response. It's going to give you a final value. And you can go ahead and monkey with your system. You can improve its operating characteristics depending upon what expected input you're going to see. So the expected input, we only talked about a unit step, a unit ramp, or a unit parabolic. Now, it doesn't have to be a unit. It could be, magnitude of 500 if you want. It's not a huge issue to deal with. The only issue is just making sure you understand what the input is, because the input will help you understand what kind of error can I expect. So I need to know the input, and the other important characteristic I need to know is the system type. The system type tells you the number of integrators in your system. An integrator is a pole at S equals 0. Its whole purpose in life is to take whatever the input signal is and go ahead and keep integrating until that input goes to 0, right? So you can start to see or start to comprehend that if I have a device that is trying to force the input to go to 0, then there's a possibility that I'm going to have pretty good error. I mean, pretty minimum error. The issue, though, is because what if I have a system that is so fast that I can't keep up with it? So then you need to start adding more integrators. And so that's why we can have type 0 system, type 1 system, and type 2 system. And so we develop these constants based on first the inputs, right? So, well, not really the inputs, more about the system itself. So we defined our K sub P constant, which is a proportional or position constant. And we find that by taking the limit of GH. And if you remember, GH is the open loop gain of the system, not the closed loop. It is the open loop gain of the system. And so taking the limit as S approaches 0 of the open loop gain will tell us what our position constant is. All right. If you take the first derivative of position, you get velocity. So we go S times K sub P equals KV, right? So taking the first derivative of position gives us velocity, which means we multiply our K sub P times S. So all we need to do is multiply our loop gain by S. Still take the limit function as s approaches 0, and we do our approach. And if we want to get the acceleration constant, we just take the first derivative of the velocity constant, which means multiplying our open loop function by s squared, not s, but s squared. And we take the limit as that approaches, s approaches 0, and then we have our acceleration constant. So the way that you solve for a steady state error is you have, first thing, what type of system do I have? Do I have a type 0, 1, or 2 system? Okay. Once I determine that, then I look in that column. So if I have a type 0 system and I'm given a step input, then I'm going to go ahead and calculate what my K sub P is. My K sub P term is right there. That's going to be a constant value. All right. So K sub P is equal to a constant, or the limit as s approaches 0 of the open loop gain. And then my steady state error is just going to be 1 over 1 plus K sub P. All right. I don't have to do any work for the ramp and the parabolic, because I can look at this table and I can tell you right off that KV is equal to 0 and KA is equal to 0. And correspondingly, my steady state error is just going to be equal to infinity in both of those. All right. If I move over to a type 1, I can see that I don't have to calculate K sub P. I'm going to get infinity when I do my limit function there. And my error is going to be 0, which tells me that for a type 1 system, if I have a unit step input, over time, that system is going to match what the input is. So I'm not going to get any error there. If I have a ramp input, that type 1 system is able to keep up with it, but it's not able to close the distance entirely. So we're forced to have some steady state error. So we calculate K sub B, and we grab that from here. Then our steady state error now is just 1 over that K sub B term. You don't need to calculate K sub A. You know what it is. It's going to be equal to 0. And then finally, for a type 2 system, which means it's got 2 integrators, that it's got no problem keeping up with a step or a ramp input. So the proportional or the velocity constants, position of the velocity constants, are both going to be infinity, which means our steady state errors are going to be equal to 0. It can kind of keep up with a parabolic, but it's not able to close the gap entirely. So I'm going to get some error. So I can calculate my K sub A, which I'm going to drag, use that over there. And then my steady state error term becomes 1 over K sub A. Right? For what it's worth, on the test, oops, why don't you wake up? I'm going to give you this table. That'll be included with the table. And I also included all the way up to K sub J if you wanted to do a type 3 system. So really that table that we just looked at is really this right here. It has this part. And you'll notice I use K. That's because K is just a magnitude multiplier. So I don't actually have to use a unit step function for that. But I actually show you what K sub P is if you are able to calculate it, or K sub B, or K sub A, or even K sub J. So I added that to this table that I have all those terms. If you can't calculate it, because it's going to equal to 0 or infinity, right? I mean, I guess you can calculate it, but it's not going to be a number. It's going to be either 0, it's going to be a 0 or infinity number. It's not going to be a, I don't know, an integer or a real number. Then I showed you what those numbers result. And then lastly, I actually show you the calculation for what the actual steady state error is. Okay? That's what's going to be provided to you. So it's essentially taking these, pieces, which shows the K sub B, K sub B, K sub A, and the table, and it just kind of combines them all into one table. All right. We're going to assume that the feedback is unity, and it doesn't need to be, but if you really want to calculate the error between what you're telling it and what the feedback value or what the output is, you really need to feed back what the value is. So if it's not, then you got to go ahead and add that K. Remember how we just subtracted we had to subtract, not add the K. We had to subtract the value of feedback and then add it back in so that we get 1, so they cancel each other out. Essentially, when we looked at it, we have a forward gain, and then what we did is we put a minus K, and this is our original K. So we had to subtract, we had to add K over here, was the way that we could force it to have a unity gain. All right. But if you do use, excuse me, if you do use a system where this is G and H, it's much harder to write on Adobe, then it's no longer the actual error signal. It is the actuating signal steady state error. Okay. So it's a little bit different term. All right. But again, you can go ahead and do that. All right, that was steady state error, which is not a super advanced topic, but it is a topic that we will use in control systems. Remember how we looked at the FE review manual and we were able to see how that's used there. The next topic is polar and rectangular math. Why polar and rectangular math? Because what we've learned is when we're plotting pole zero maps, we have complex numbers. And we have poles and zeros that if we plug in certain numbers, it's the possibility of getting actual vectors that we have to do. And so what we wanted to do is make sure that we have M1 theta 1 times M2 theta 2 divided by M3 theta 3. From a polar math perspective, that's M1, M2, all over M3. So we multiply complex numbers. We multiply the magnitudes when we multiply complex numbers, and we divide the magnitudes when we divide complex numbers. And then the angles are, when we multiply, we add theta 1, sorry. We add the angles, and when we divide, we subtract the angles. And the reason why we did that is because when we saw what we looked at the characteristic equation, which we said was 1 plus kgh, for that to be a valid root, that has to equal 0. So immediately, we realize that the magnitude of kgh has to equal 1, and the angle of kgh has to have some multiple of 180 degrees, right? For that to be a valid root, for that equation to work out, we have to go ahead and do that. And so we did a fair amount of work to get our results, okay? And now, when we want to solve for our value of k, so let's say that we have a root that we know is valid, and we want to solve for that value of k, that gives us that root, we can solve for that value of k just by using this equation here. And you'll notice it's 1 over gh. What happened? Because when I did my calculation over here, it looks like k should be equal to -1 over gh. Well, the reason why it's here is because k is purely a real number. So we have to do the magnitude calculations for k to calculate k, and the angles have to work out so that you're going to have that plus or minus 180 degrees. All right. So whatever we need to do, we can solve for k, hopefully pretty easily that way. So that is, again, if you want to solve for a particular value of k, so that's a design parameter, you're specifying a value of k to meet some criteria to actually specify that k. This is the root I want because this is the performance characteristics I'm looking for. I'm going to go ahead and I'm going to spit out, hey, these are the results. This is the value of k, and now I need to calculate it based on a valid pole that I'm looking for. Next thing about root locus is start at a pole and end at a zero, right? So that's our mantra or rule number 2, if you're following along with the notes. So starting at a pole means we start at a finite pole, and we have to have finite poles, right? We can't have no finite poles because then the system wouldn't really be real. So we start at a pole and we end at a zero. And in all the systems that we'll do in this class, you'll always have at least the same number of poles as you do zeros. So you'll never have to start out at a pole at s equals infinity, all right? So we start at a pole and then we end at a zero. And that allows us to draw a root locus or at least know where that root locus is going to terminate, all right? So just because we start at a pole and end at a zero, that doesn't mean we have to leave the real axis. Remember, one of our first rules is we had to have symmetry about the real axis for root locus. So we need to make sure we have complex conjugate pairs. So if you only have one root locus on the real axis, you don't have another one, you can't leave the real axis. It has to terminate. So if you have something that looks like this can't exist like this. You can't, well, no, you can go like this, but you can't leave and go off into that realm. All right. So let me show you another example. So on the real axis, what happens here? I start by labeling my poles or zeros on the real axis, odd and evens, right? And we know that it always lives to the left of an odd number. So we know that it goes here, right? But not here. And then over here. And there is no finite pole to that. So you can say, hey, wait a minute, Paul. I know that I need to start at a pole and end at a zero. Well, that's okay. I'm going to break away. And one terminates here. And one goes way out at s equals infinity. So by using that mantra, starting at a pole, ending at a zero, it helps you understand at least a little bit how to draw these. Now, if you had something that looked like this is much harder. And the reason why it's much harder is because you don't know, am I going like this or this? You know, you just don't know, but you know that both sides have to be the same. So let's say it does something like this. That's okay, as long as, again, we have symmetry about the real axis. Because we start at our pole and we end at our zero. All right? So we already talked about being to the left of an odd polar zero on the real axis. That's where it lives. If you have to go off the real axis, or even if you stay on the real axis, if you have to approach a zero as s approaches infinity, then at that point you have to calculate asymptotes. So the angle of the asymptotes is just r times 180. And I should have defined this. Remember what r is equal to. It's m minus m. This is the order of the numerator, the denominator. And that's the order of the numerator. Okay. So that's n minus m. So if you have 4 poles and 2 zeros, that means you have 2 zeros at s equals infinity, which means you have to have 2 asymptotes. All right. So now you can go ahead and you can stuff in. I've got 180, my r. And then I'm going to have my next one, which actually I have to skip, right? So it's only if it's an odd number. So I've got, basically I have the 180 is what I would end up being, okay? So then I take r at 180 and then I divide that by the number of finite poles and the number of finite zeros. Again, so that would be 2. And what I would end up with is 90 degrees. This r here, right, when I do the calculation, This has to be, from this approach, it has to be an odd number. Why can't it be an even number? Well, because if R was an even number, then when I have 180, then I would get 360. The problem with 360 is that is not going to make the equation 1 plus KGH equals 0. So this only can be 1, 3, and it's plus or minus 1, plus or minus 3, plus or minus 5, all the way up until whatever value you have. But you won't end up with any even numbers. You'll only end up with odd numbers. So that's why we only have 1 and not 2. So that's the angle of the asymptotes. And then the centroid of the asymptote, where the asymptotes actually start. And again, that can be any place. That's going to be on the real axis, but it's going to be any place. And the reason why it's any place is because that's where the root loci approach the pole of the 0 at s equals infinity. So it can be, if I'm over here and I have a valid root locus that goes over here, I can have my centroid over here and that works perfectly fine. All right, doesn't matter. That's not an incorrect calculation. It just means that your centroid starts there. Now, if I have two poles on the real axis and they're heading towards each other, I know that I'm going to have to break away. Where do I break away? I take the partial derivative of k, where remember, 1 plus k gh equals 0. So you solve that for k. Take the partial of that with respect to s because we're looking at a maximum or minimum point. And then we can go ahead and solve for that value of k. The k that you get, it's possible to have multiple points. So now what you need to do is, all right, that value of k that's valid has to live where the root locus live. And the reason being is because that's where the actual root loci break away from the real axis. So you can't have a k point that is someplace where there's no root locus because they're not breaking away. It doesn't exist in that location. And so we talked about that. Let me move this out of the way. If you have complex poles or complex roots, right? These are finite poles or finite zeros. Then you have to calculate angles of departure or angles of approach. And a departure angle is when you're departing a root. And an arrival angle is when you're going to a pole. Why is that? Because we start at a pole and end at a 0. So if you're confused about, am I calculating theta D or theta A, just go back to your mantra. Start at a pole, end at a 0. Start at a pole, end at a 0. All right? That really will help you because when I draw these root locus, and even when we do our calculations, right, we're all basing it on a couple things like how did we calculate angles and all that stuff. Well, it really helps us. Oh, we're just trying to solve this for this value. How do I draw this? Well, I know I started a pole, so you can actually start to envision what's happening and how you set that up. All right, 5 little questions. So given a root locus plot, I'm going to give you the root locus plot. Give me the open loop transfer function, GH. So this is not necessarily, is the system bistable? This is, tell me on a pole 0 map, if I have some design criteria, what areas on my pole 0 map would I find, a value of k or poles that would meet those design criteria. So remember we talked about second order systems and how we plotted those, and we looked at zeta and omega sub n and omega sub d, and then the damping coefficient. That might be really helpful to understand what you're doing for that. Now I'm going to actually draw a root locus. So I'll go through all those rules. If I give you a block diagram, give me some steady state errors. And then I'm going to use it as a design. So I want to limit my steady state error to a certain value. You have to pick the value of gain that meets that steady state. This is the other thing I will give you. So this is just a little more description as opposed to the rules that we had. This is just, you know, if you want to figure it out with the actual text description, you can see here, like the first one, the K equals 0 points. This is another way to say what? Start at a pole, right? And K equals 0, that's starting at a pole. K equal infinity and at a 0. This one is a good one just to kind of give you a clue. How many branches or how many root loci do you have? You have the same number as finite poles, right? So poles, not zeros, poles. You got to be symmetrical. So this was our rule 1. Remember our rule 1? Asymptotes, well, that kind of goes, but that as K approaches infinity, as you're getting further and further away, you start to approach those infinite zeros. So you might need to calculate asymptotes. If you have the same number of poles and zeros, don't need to do those two, right? Because you have no infinite zero. So why would you calculate asymptotes if you don't need to do that? This over here is to the left of odd polar 0. The next one, intersection of the root loci with the imaginary axis. This is our auxiliary equation from Ruth Hurwitz. And you just take the roots of the auxiliary equation, right? We did that in last class. And then here's the breakaway points. And instead of calling it K, I actually showed you what you're calculating. So again, if you have something that does this, right? And I should say, if it goes like that, you don't have any breakaway points to calculate because there are no root loci that leave the real axis. So again, to understand how to draw these things, it's really helpful to go through in your mind, okay, what's the process? It's find the poles and zeros, right? That's usually the best thing to do. Step 1. Step 2, put on your pole 0 map where all the poles and zeros exist. Well, maybe we'll write that down. So step 1, find P's and Z's of open loop gain, right? Step 2, draw P's and Z's on pole 0 map. Step 3, so this is where now we have to start using some of the root locus rules, right? Find real axis root loci using RL exists to the left of P's slash Z's on real axis. Okay, so these first 3 steps are really helpful because this kind of gives you, all right, now I know kind of what the root locus looks like. Now I have to start deciding, do I need to calculate? So I'm going to put 4 question mark. Calculate asymptotes? Maybe. But if you don't have any infinite zeros, you don't have to calculate any asymptotes. So you can't really write a step-by-step process, right? Because step 4 might not even exist if you don't have any asymptotes. You don't have to do anything. Step 5. Find break-in / breakaway points. Again, if you don't have a root loci on the real axis between 2 poles, you don't have any breakaway points or break-in points. because you never leave the real axis, right? So again, I can't write that step-by-step process. Step 6, find J omega crossings. Do I need to do that? What if it doesn't cross the J omega axis? Then I don't need to do step 6 either. So this is why this one is a lot harder to do root locus, because it relies on you, the student, to be able to say, do I need to do this or do I not need to do this? Right? Where in the past, it's like step 1, step 2, step 3, step 4. Okay, I'm done. Over here, it's step 1, step 2, step 3. All right, do I need to do step 4? Maybe, maybe not. Same thing for 5 and same thing for 6. So that's why it's really important that you understand the process for how to do this. And then the last sort of step, if you will, find, K that meets your design criteria. Because again, we're not just drawing these root loci just for it's good for our health. We're drawing these because we're told, our boss told us, you need to design a system that meets these design criteria. And she knows you're a competent person, so here you go design it. All right. Same thing with steady state error. Same thing with percent overshoot or settling time or rise time. We're changing, as opposed to just crank the wheel and then turn out results. We're changing to, all right, here's some, some factors to consider, which is what engineers do in most of the time in the quote unquote real world. You have to have some engineering judgment. Some of it is not as cut and dry as perhaps this. Like I was talking to Zach Atherton the other day, and I said, if you had to go do a line-to-line test, line-to-line, you have to do a relay that protects a line. And so you have to do end-to-end testing to make sure everything works. I'm like, how long would that take? He said 4 hours. I was shocked. I was like, wow, you're really good at this. But the reason why is because he's done a lot, but he's hoping that there's no tricks. What happens if the fiber isn't configured correctly, or they're getting the wrong signals in? That's when you have to start using engineering judgment to how do I modify or monkey things? Or even more importantly, hey, Zach, I want to design a substation that meets criteria. Here's a blank sheet of paper, start designing it. That's when, all right, well, what are your design specifications? If you ask them which was harder, the end-to-end tests or designing a substation, I would wager that he would say it's designing the substation, because what are your design criteria? How I design one thing might be different than the way you do. But as long as I meet the criteria that you want, then we should be good to go. Unfortunately, in the real world, though, everybody's got standards. So you design things to a standard, right? The way, let's say, Versant does things, it's very specific. They want these type of equipment, this type of protection, yada, 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 because they have a whole system that's been designed a certain way. It has those criteria. It's the same thing if you design the next iPhone, right? Apple's not going to go in and reinvent their software. So it has to have whatever you put on the phone, it has to be able to work correctly with the software. So they've got standards for how this equipment has to operate and function. And then there are limitations on that. So again, that's why this class is quite a bit different in terms of, how we do things. But we'll get you ready for the FE. Big pay raise when you get it. I didn't get a pay raise. When I got my PE, I didn't get a pay raise. When I got my PE, I did it on my own. I got my PE. I took a day of vacation, take the PE, because it's, I don't know if it still is, but it used to be during the week where the FEs were on the weekend. And I just did it on my own. And once I told them I passed the FE, oh, make sure you put on your business card. Well, is that a big deal? Yeah, that really is a big deal. Well, you can pay me more? No, it's not that big of a deal. But, change your business cards, that's a big deal. But I'm saying that a little bit in jest. But again, this is a good thing. And I know that some of you folks don't like the fact that we have an FE review class and that you have to take the FE, but it just gives you that option. And as some seniors in this class are graduating, You just want as many options as possible when you get out. Because if you know exactly what your career is going to look like for the next, either hopefully or not hopefully, maybe you old folks are fire folks. I've talked about that term in this class before, right? Fire, financial independence, retire early. Nobody's heard that term? Man, you got to get on TikTok. That's all over. So the idea is people save like 80% of their income. I don't know if it's that high, but it's pretty high. And they work hard. And by the time they're 40 something, they retire because they've got, I don't know. What's a lot of money in the bank? 5 million, $3 million? Yeah. At this point, yeah. So let's okay, let's say $5 million to make it easy. You got $5 million in the bank and you can live off that for the rest of your life. Not a lot of people do that, but even those folks who are really motivated and have an insight goal, you know, their lives, how they get there is going to be very different. You might have to do a different job. You might have to learn. You might get laid off. You know, with what's happening politically now, you just can't predict. So it's really good to have, you know, something in your back pocket. If you work in one industry and it doesn't work out in that industry, you go to the other industry. Hey, I've got my FE and perhaps even my PE. And you put that on your resume because somebody who looks at that, and especially in engineering technology, because our engineering technology program at UMaine is excellent. It's really top notch. And we turn out great students that are ready to work and do really good things in the world. Some of the other engineering technology programs in the rest of the country, well, you know, it works for them. Let's just put it that way. But there are companies that won't hire engineering technology students because some of those other universities, you know, they're kind of tossing people out that don't have great capabilities. But when they see, hey, you passed the fundamentals of engineering, I thought only engineers could do that. Well, I am an engineer. Just because my degree says engineering technology, that means my focus was different. That doesn't mean I don't have abilities and competencies that, you know, graduates from engineering programs do. So having that as your backup, again, kind of evens the playing field. And I'm not saying that to put anybody down. I'm just pointing out, like, this is just, again, another accolade that if somebody says, well, we don't want to hire you because you have an engineering technology. So but I have the fundamentals of engineering, which means I'm at least as competent as many of the other engineers that are here. So what are you talking about? And it's usually only that first job or two that make a difference. And then once you get your PE, you know, if it says PE, I don't even think they care where you graduated from. You could have went to MIT. You could have gone, if they're looking for PEs, oh, great. You went to ABC USA University. I just made that up. I don't know if it exists. I just made that up. They don't care. I'm a professional engineer in that state. Okay. What's your background? What's your experience? It's what we want. All right, you're hired. Nobody will look at your degree. But, you know, like I said, those first couple make a difference. All right. Sorry about that. I got off on a tangent, but I'm trying to see, because some points of this class, a lot of you were like, why are we doing some of this stuff? What's the point of this stuff? Well, a lot of it is just very broad skill development, not just doing circuit analysis and understanding how to do this, that, and the other thing. A lot of it is like, we're trying to get some general approaches to solving engineering problems. Doesn't matter if it's electrical, mechanical, chemical, civil. If you have an understanding and a background, help out. You just made yourself more valuable to the company. If I know how to do a little bit of mechanical stuff, wow, I'm a lot more valuable to the company than if I can just do electrical. Oftentimes you'll be put in electrical, but I know electrical engineers who do nothing but civil design. They lay out transmission lines. That actually, their work actually has nothing to do with electricity. Because you hang out a transmission line, you got stresses and strains and forces and all that stuff. Hey, where do I use Ohm's law here? You know, it doesn't apply, right? But what you're doing is all those dynamics, all those statics, as long as you have that understanding, you can design transmission lines. As a matter of fact, becoming a professional engineer, at least used to be, I don't know if it's still the case, but I believe it is. Jude would be a better person to ask. If I say professional engineer on my stamp, I can stamp a document. It doesn't say professional engineer electrical, which would imply I can only stamp electrical drawings. It says professional engineer. I stamp a drawing. I'm saying that on that drawing, I personally ensure that the contents of that, let's say, document are consistent with best practices. I don't need to be a mechanical engineer to stamp a mechanical drawing. Again, that you'd have to double check with Jude, but I'm pretty sure it just says PE. You can stamp it. It does keep track of discipline because like mine, it says electrical. But I think when you're looking at stamped drawings, oh, Paul Villanova stamp 1, 2, 3, 4, 5, 6. It's stamped. It's gone for it's gone to the public for decision. They're not going to look back and say, all right, no, he's got the wrong certification, X that drawing. It just looks to see if it's stamped. Leo?
I was just gonna say, the FD class, I believe it was.
What's that?
The FD, that, it doesn't say what it's, but it just says like.
Yeah.
FD.
Well, I'll show you mine. I'll show you how old I am. Because this is when I got my first, I was living in Virginia. So. This is my first PE, because like I said, I took the test and I got it. So license search. Just type in my last name. There I am. Oh, what a long license number. I said 1, 2, 3, 4, 5. And it says here license type. It says professional engineer license. Does it say mechanical? But let's dig down in here. And there you go. It expired because I'm inactive because you have to spend $200 a year every year or two to do it. So I have my main one. But does it tell which discipline I'm in? No. So in Virginia, I can stamp it. I can stamp any mechanical, I can stamp any civil, I can do any one of that. And like I said, you can see how old I am because I've had it since 1999. So yes, sir. What's that? Yes. Yeah, so you can only stamp a drawing if you have an active license in that that jurisdiction. So my PE license in Maine is active because that's where I would be most likely to stamp drawings. But if I wanted to do work in Virginia, I mean, I could reactivate it. Usually going to send in a few bucks and maybe send in a couple pieces of paper and then they can reactivate it. But yeah, that's how you do it essentially. And I always get a kick out of it because it used to be really good. Like the way you could tell how long you had a PE was a thing of pride. But you can see my number is 32,598, which is lower than Randy Villanova, but I have no idea it is. So that means I've had my PE longer than him. I don't know what the 0402 is. That probably is just like a designation for PE. But you can see that my number is sequentially lower. So I had my PE a lot longer. So what do you think of that, Randy? Same thing in Maine. My PE license in Maine, it's 10,000, but I didn't get it until 2004, I think, in Maine, because I wasn't living in Maine. I didn't need it. So anyway, the other thing that's interesting too, and I always get a kick out of this. So getting a PE is kind of a big deal. And I'm not putting anybody down, but I would imagine to get a cosmetologist license might be a little easier than getting a PE. So again, it's not putting that person down. It's just like a level of effort, but I get the same certificate that a cosmetologist would get. So you think, oh, I'm a professional engineer. I did 4 years of school and got this test and then did another test and worked for 4 years. And I did all this stuff. So this took me at least 8 years to be able to get this. I have a lot of pride, but they're like, no, it's the same piece of paper as the cosmetology one. It just says a different word on it. I was like, oh, okay. So you don't want to hang these licenses. They don't look like that big of a deal. So anyway, enough jokes. All right, I'll shut up now. I've been yapping for almost 45 minutes. Any questions on the tests? Matt?
Well, as more about what we covered here. We were talking about how you draw a line in the root of squat, you draw a line from the pole to zero.
Started a pole, ended a zero. Yep.
Does the direction of that line that actually important, or is that just telling you where the line?
It is important because remember, if I have this, right? I'm starting here and starting here. Where are they ending? They can't. They can't end in the middle. Because I only can end at a zero. So I can only end at a zero. Same thing over here, right? If I had this and I had this, those are endings, so those are going this direction here. But I have no place to start. So at some point I have to come in like that. Now, if I have this, I started at a pole and ended at a 0. So giving you those directions will tell you, do I have to calculate break-in points like this or breakaway points like this last one? I don't, but you see these other two, I have to start doing more calculations. So arrow is helpful to know what the root locus looks like for sure. Any other questions? Go ahead.
In the very first part, error probably.
Steady state error, yeah. The system types? Sure. So remember, this is my loop gain. That's G times H. That has some numerator and some denominator, right? If I can factor S out, then the system type is indicated right there. N is the system type. Right? So if you factor out S and you have an S multiplying up front, then you just go ahead and do that. And N can be equal to 0, right? What is S to the 0 equal to? 1. So if I don't have any integrators, that still works out, right? It just means that my S is raised to the 0 power. So all you need to do is look for the S terms. Remember, this is a pole at S equals 0, or look for the root of the denominator term for your GH. That's the system type. That answer your question?
Yeah.
Okay. Other questions? Anybody in TV land? Going once. Twice. Third time. No buyers, no whammies. Anybody know who Wink Martindale is? He was even before my time. That's how old he is. He died at 91. He was a talk show or game show host, I should say. And there was games, no whammies, stuff. These were like these in the 70s and 80s, the games they had. I don't know if they still are that crazy, but you would have people act like complete fools. And that was one of the games. No whammies, no whammies. I don't even know what a whammy is, but that was one of the lines. So take a look on YouTube. No whammies, stop and see this classic stuff. But Wink Martindale just died like last week or this week, maybe. 91, he had a good life. All right. I will really stop talking because everybody's gonna be like, what are you talking about? All right, folks, if there's nothing else, have a wonderful day. And I will see some of you all shortly. Take care, everyone.
See you, Paul.
See ya.